This is the solutions to exam number 4. Most of these solutions I would have expected you to use the calculator to optimum effect, but I will show the problems both ways. Our first problem is about profit, and it says that the rate of growth in the profit in millions of dollars, that's very important, from a new technology is approximated by p prime of t equals t times e to the negative t squared. And t represents time measured in years. And it tells us that the total profit in the third year that the new technology in operation is $10,000. And we are to find the total profit function including units, which means that we're going to include the idea that the total profit is in millions of dollars and t is the year in which that profit is made. So the total profit function is going to be the parent function of this derivative, which means it is going to be the integral of p prime of t dt, which is the integral of t times e to the negative t squared dt, which is more easily integrated if we first rearrange this into e to the negative t squared and put the t over here with the dt, because this is going to be a u substitution problem. And u, in this particular case, is going to be negative t squared. Which means then that du is going to be negative 2t dt. Which then tells us in order to have negative 2t dt, we need negative 2 here. But we also are going to have to include a negative 1/2 factor on the outside. So then in order to do that integral, we're going to get negative 1/2 times the integral of e to the u du, which is going to give us then, back in the original problem, negative 1/2 times the integral of e to the negative 2t squared. I'm sorry, the negative t squared, not 2t. And then that gives us the negative 2t dt. So the integral of u, e to the u, is going to be, of course, e to the u. And then the 1/2 is your hitchhiker, your multiplier, and it just drops right on down, which, since u is negative t squared, then that becomes negative 1/2 e to the negative t squared plus the constant. And it's at this point now that we need to go back and remember the extra piece of information that we were given. And that extra piece of information is that P of 3, the total profit in year 3, is $10,000. But remember that total profit is in millions of dollars. So that doesn't mean that your constant is 10,000. Your constant is actually $0.01 million. So we're going to use that fact by saying that $0.01 million is the total profit in year 3. In other words, where negative 1/2 e to the negative 3 squared plus the constant, which then gives us that the constant is 0.01 plus e to the negative 9. And for that, we'll use the calculator. And I forgot my 1/2, so we need to multiply e to the negative 9 by positive 0.05. I'm sorry, 0.5, not 0.5. Positive 0.5. Just to make sure that we get the order of operations in the correct order. And that comes now to be, your constant is 0.010061749. And since that is in millions, that is not actually a whole lot more. Millions will be 6 decimal places, so this would be $10,061, or $62 if you round it up to the nearest dollar. But in terms of millions of dollars, that isn't really that much difference. So we're probably just going to stick with the fact that it is 0.01, because in year 9, the additional profit was negligible. It really was. So that means then that our total profit function, P of t, in reasonable terms, is negative 0.5 instead of the 1/2, because that's easier to deal with, times e to the negative t squared plus 0.01. And then it says, what happens to the total amount of profit in the long run? Well, you can graph P of t, or you can graph the rate of change and interpret from there. But the idea here is what is happening to P of t as t approaches infinity, or as time goes on, as t gets larger. And what we see happening, we actually kind of got an idea of here, is that in year 3, profit had gone from $10,000 to $10,062. And that's because as t approaches infinity, for 0.5, which is negative, e to the negative t squared plus 0.01, well, this doesn't change. Regardless of the value of t, that doesn't change. But what happens to this is that as t approaches infinity, this approaches 0. As time goes on, that actual marginal profit decreases to nothing. That's actually what that is marginal profit. So what happens is that as time goes on, P of t levels out at about $10,000 every year. And this is a problem out of chapter 15, I think probably 15.1. Our second one is a cost analysis problem, and this cost analysis problem actually goes all the way back to chapter 12. And when you go all the way back to chapter 12 with this problem, you're talking about what is going on with the cost itself and where is the cost discontinuous. So the first thing we need to come up with is a cost function. So the company charges $1.50 a pound when a certain chemical is bought in lots of 125 pounds or less. And the price per pound drops to $1.35 if more than 125 pounds are purchased. So that tells you you've got a break at 125 pounds. So when X is equal to or less than 125, then your cost is $1.50 per pound. But when your pounds purchased is greater than 125, your whole quantity, then you get a price break and it drops down to $1.35 per pound for the entire amount, including the initial 125 pounds. So this is your C of X function. And C of X is in dollars for X pounds. So the answers to A, B, and C are pretty straightforward. If X is equal to 100, C of 100 is simply $1.50 times 100, which is $150. And for 125, it's $1.50 times 125, which turns out to be $187.50. And for part C, if you buy 140 pounds, then for the entire 140 pounds, you pay $1.35 a pound for the entire 140 pounds. And that comes out to be $189. So then we're asked to graph C of X. Well, these points here will give you sufficient information to graph C of X, and your graph isn't expected to be perfect. So let's say this is 25, 50, 75, 100, 25, 50, 75 pounds. So at 100, your total cost is $150. So here's 25, 50, 75, 100, 25, 50, 75. That's not going to be enough, so I'm going to change this and say this is 25, 50, 75, 100, 25, 50, 75, 200, 25, 50, 75, and this would be 300. So at 100 pounds, the cost is $150. 25, 50, 75, 100, and we're going to go up to 150, which is going to be about here. And then at 125 pounds, it's at 187.50. So here's 125 pounds. This would be 175. This would be 200. 187.50 would be about right there. So this part of the function looks like that. Now for 140 pounds, if this is 125 and this is 150, 140 should be along here. And the total cost was $189. So really not much different from that. And we could go up from there, but essentially we have a slightly less of a slope here. And at 125, we see there is a discontinuity. So x is discontinuous, or c of x is discontinuous. At x equals 125 pounds. Because that's where the discount takes place. And then part F asks you to find the average cost per pound. C average of x is C of x over x. And it says find the average cost of 100 pounds. Well, the total cost of 100 pounds was 150. Divided by x is 100. And it shouldn't surprise you then that the average cost for 100 pounds is $1.50, because that is what it should cost per pound. This is a linear function. The rate of change and the average remains constant. And for that reason, then C average of 125 is that 187.50 divided by 125, which again shouldn't be a big shock that it's $1.25. And then H says for 140, C average of 140 is equal to 189 divided by 140, which is $1.35 for each pound. Because that's what an average is the cost per pound. Part I says find and interpret the marginal cost, that is the instantaneous rate of change of the cost. Well, that's C prime of x. And when x is equal to or less than 125, that's $1.50. So for 100 pounds, C prime of 100 is going to be, just like it is for every other pounds in this range, it's going to be $1.50 per pound. Because $1.50 per pound doesn't change for that entire range. And the same thing for C prime of 140 is going to be $1.35 a pound, because 140 is greater than 125, and every pound over 125 costs $1.35 a pound. So hopefully you didn't overthink that one and you got that one right. So now we move on to the in-class part of the test. Problem number 1, we're going to find the derivative using implicit differentiation. We have 7x squared, for which the derivative is 2 times 7x to the 2 minus 1, minus 2 times 4y squared would be 2 times 4y to the 2 minus 1. And then because y is a function of x, we have dy dx. And the derivative of any constant, including 24, is 0. So then that tells us that 2 times 7 is 14x, minus 2 times 4 is 8y, dy dx is equal to 0, which means 14x is equal to 8y dy dx. Divide both sides by 8y, and you come up with 7x over 2y is equal to dy dx. So for part 2, for a particular commodity, the price per unit in dollars is given by P of x equals 120 minus x squared. And x is measured in thousands and is the number of units sold. And it's valid on the interval from 0,000 to 34,000. So how many units need to be sold to maximize revenue? Well, anytime you're going to do a maximization problem, you know that you're going to have a derivative. But the thing that you need to pay most attention to here is that it says maximize revenue. This is not revenue. This is price. The way that you find revenue, which is R of x, is you set it equal to the number of units in thousands that you sell times the price of x thousand units. So that means your revenue function is going to be 120x minus x cubed over 10, or 120x minus 0.1 x cubed. And that is the function that we're going to want to maximize. So what we're going to do to maximize that is we're going to take its derivative. we're going to set it equal to 0. So the derivative of 120x is 120. And the derivative of negative 0.1x cubed is 0.3x squared. And we're going to set that equal to 0. And we're going to solve that. So this actually is very easy to do algebraically. We simply add 0.3x to both sides, or 0.3x squared to both sides, then divide both sides by 0.03. And 0.03 into 120 means that we come up with 400 is equal to x squared, which means x is the square root of 400, which is plus or minus 20. And of course, negative 20 isn't on the interval from 0 to 30, so we're only going to keep the positive answer, x equals 20. So then all that needs to be done, since we're going to go from 0 to 34, and we know there's a critical value at x equals 20, what should happen is that r prime of x should be negative on this interval, and r prime of x should be positive on this interval. And if that's the case, then x equals 20 is a maximum. So if you set your derivative in your calculator, and that's the easiest way to do this since it's just arithmetic, so your original function is x times the price function. And the price function was 120 minus x squared. And if we let y2 be the derivative of x times 120 minus x squared, then we can set the table up so that it lets us ask for values. Go look at the table, and at x equals 0 and at x equals 20, and at the other end of the interval when x equals 34, remember what you're looking at here is not the value of y. All we verified here is that the actual value at x equals 0 of your revenue is 0. But the rate of change of revenue at x equals 0 is positive, as it should be. And it is negative here, as it should be. The only thing that's a little troublesome is why it would be negative 1080 when it should be 0 for y2. So let me recheck my derivative. Nope. Okay, let's try this again. Not let the calculator do the arithmetic. Well, not all of it. Oh, I know what I did before. I'm sorry, I left out the divided by 10. and that is as it should be. So it is positive here, 0 at the critical value and negative on the other side. So if I had done that correctly, x times 120 minus x squared divided by 10, then that is the values that we would have gotten. Got to be careful how you enter your functions. Not leave anything out. So then our next problem is a revenue problem. And we have that the revenue for the dog houses is 12,000 times the natural logarithm of 0.01x plus 1. And says use the differential, and at this point you should know differential means derivative. To approximate the change in revenue from the sale of one more dog houses or doghouse when 100 dog houses are sold. So all we need for this then is to take the derivative of r of x. And this is a U substitution problem, or a chain rule problem, which is where U substitution comes from. So it's going to be 1,200 because that's your multiplier. I'm sorry, 12,000. And the derivative of the natural log of anything is going to be 1 over whatever that is. But since this is a function, we need the derivative of that function, and the derivative of this function is 0.01. So what you're looking for is r prime of 100. So you can either do that much arithmetic, or you can do your numerical derivative. And for this one, I will actually use the TI-84 since some of you have the 84. And the function is 1,200 times the natural logarithm, or 12,000 times the natural logarithm of 0.01x plus 1. And what I will want is the derivative of that. With respect to x, for any value of x. And then I have two options. I can go to the table as long as my table is set up to let me ask, and it is. Okay, so it helps if you actually put in the correct function and not the integral, but the derivative. So now we can either go to the table. You're so contrary. And start out with 100, which is what we actually wanted, so we can not even look at the rest of these. And what we see is that the price of one additional doghouse is going to be $60. And that if you do y2 of 100, it is $60. You can also do that with the arithmetic, but I'm not going to take up time doing that at this point. So what that tells us is that r prime of 100 equals $60. And the interpretation of that is that the sale of the 101st doghouse will increase revenue by $60. Our next problem is out of 15.4, talking about the elasticity of demand, and you have an expression for the demand for distilled spirits. Quantity is a function of price, and the quantity is negative 0.00375 times P plus 7.87. P is the retail price of a case of liquor in dollars per case. So Q is going to be the average number of cases purchased per year by a consumer. To find the elasticity, we take E is equal to the opposite of the ratio P over Q, and since Q is negative 0.00375 times P plus 7.87, we need to multiply that times the derivative, dq dp, but dq dp, since this is a linear function, is just the coefficient of P. So that means the elasticity equation, negative times negative, is positive 0.00375 times P over negative 0.00375 P plus 7.87. So E, when the price is $144, we're simply going to substitute in $144. And E actually turns out to be less than 1. It is 0.073. which tells us that at $144, demand is inelastic. And what that means is that a small percentage increase in price will create a small percentage decrease in demand. And in order for that to make a little bit more sense to you, what actually happens is that if you take a 10% increase in price, let's say, then what happens is that the elasticity is actually a coefficient. And it means that your actual price change for your liquor is only going to be about 0.07%. So the price would have to actually increase quite a bit before it would actually impact the elasticity of the demand and make it become elastic. So the next couple of problems are fairly straightforward integration problems. Number 5 is simply to use the power rule. So we will integrate each term, one term at a time. The integral of 5x squared is 5x to the 2 plus 1 over 2 plus 1 minus 6x to the 1 plus 1 over 1 plus 1 plus 3, and remember that's actually x to the 0, so we add 1 to it, which tells us then that since this is 3, 2, and 1, then we have 5x to the third over 3 minus 2 goes into 6 3 times, so that's going to be 3x squared and 3x plus 3x plus a constant. So that tells us that whatever the parent function was, it was 5 times x cubed over 3 minus 3 times x squared plus 3 times x plus the constant. The integral of 4 over x cubed is better written so that you realize what you need to do as the integral of 1 over x cubed with the 4 on the outside. And then since 1 over x cubed doesn't give us a negative power when we take it out of the denominator, what gives us a negative power but doesn't give us negative 1, we're going to say that that's x to the negative 3 power dx. So then our integral is going to be 4 times x to the negative 3 plus 1 over negative 3 plus 1 plus a constant. And since negative 3 plus 1 is negative 2, and negative 2 goes into 4 negative 2 times, we have negative 2x to the negative 2 power plus c, or negative 2 over x squared plus c. Either answer is just fine. And both of those problems come out of section 15.2 if you need to review those kind of problems. Number 7 is a definite integral, so it comes out of 15.4. And all we're doing differently here is you can use your calculator to do this, or you can do the integral using your power rule. So using the power rule, if this is u, then du is equal to 1 dx, so we don't need to really do any substituting. So that tells us that we add 1 to the power, and then divide by that new power. And we're going to evaluate at 5 and at 0. Now, I can't tell you how many people I saw that went to a lot of trouble to say that this was going to be the integral of x squared minus 10x plus 25 dx. And if you did it that way, that was perfectly fine, but you did a lot more work than you needed to and didn't realize it. Sometimes it's easier to take the obvious way out, because in this case, 2 plus 1 is 3, and 2 plus 1 is 3. So what we actually have here is x minus 5 to the third power divided by 3, and we're going to evaluate it at two really simple numbers, 5 and 0. So all you really needed to do from here was plug in 5. And then plug in 0. And 5 minus 5 is 0, and 0 cubed is 0, and 0 over 3 is still 0. Minus 0 minus 5 is negative 5, and negative 5 cubed is negative 125. And since negative times negative is positive, then your answer was 125 over 3, or you could write it as a mixed number or a decimal. And either one of those was fine. So this was a lot shorter solution than about half page that most of you went through doing it this way. This way works, but it's the hard way. So I'm glad you had the algebraic talent to do it that way, but you did a lot of extra work that you didn't really need to do. So then number 8 says find the cost function, which would be c of x, given the marginal cost function, which tells you this is a derivative, and the notation indicates it's a derivative. So that's going to be the integral of 4x minus 5 dx, and it goes on to say the fixed cost is $8. Which just simply means that if x is equal to 0, then the cost is $8. So integral of 4x minus 5 dx is the integral of 4x, which is 4x to the 1 plus 1 will be squared over 2, minus 5 times x over 1 is just going to stay 5x. So 4x squared over 2 is 2x squared, minus 5x plus a constant is going to be equal to 8 if x equals 0. And of course, if x equals 0, those two terms disappear, and that tells you that your constant then is 8. So then your cost function, c of x, is equal to 2x squared minus 5x plus 8. Now, problems 9 and 10 are both out of section 15.2, and they require u substitutions. The first thing I'm going to do is I'm going to rewrite the problem so that it's easier to figure out what u might be. So if you look at this, that e to the 2x plus 5 is down here in the denominator, and its derivative is 2e to the 2x. Or at least that's part of it. So what we have is 1 over e to the 2x plus 5 times e to the 2x dx. And if we choose u to be the part that's in the denominator, then du is equal to e to the 2x times the derivative of 2x, which is 2, or 2e to the 2x dx. So what we have is the e to the 2x. What we don't have is the 2. All we need to do is plug in the 2 on the inside and plug in 1/2 on the outside. So that what we have now is 1/2 times the integral of 1 over u du. And you cannot use u to the -1 power. There was a mistake in my answer key, and I apologize for that. And I did not count this problem wrong for anyone. If you did something that made sense and then wrote down my answer, even though you should have arrived at what I'm about to arrive at. So the actual answer is 1/2, and the derivative of 1 over u is the natural log of u plus a constant. And then to put it back in terms of the original problem, this would be 1/2 times the natural logarithm, and usually we do the absolute value, although in this case it's redundant. The natural logarithm of e to the 2x plus 5 dx turns into the constant. And the reason you can put in the absolute value bars is because you need that to be positive. You can't take the natural log of negative numbers, but they are kind of irrelevant, because even if x is a negative number, then e raised to that power is just going to be a fraction. It's never going to be equal to 0. 5 is always going to be larger, so this is always going to be positive anyway. But the absolute value bars are just a safety measure. So now we have our last problem. And again, I'm going to rewrite that problem a little bit, because I'm looking at x raised to this really complicated power and thinking, you know, probably that power is going to wind up being u. So this is what I'm thinking. So if that's u, then du is equal to 6x dx. Now I noticed several of you tried to take u to be x squared, and all you did was cause yourself a world of hurt when you did that, because it didn't work out to be anything close to what you wanted it to be. You got mixed up in the simplification, and you did not come out with the right answer. So remember, take u to be the most complicated part of it that you can figure out. And most complicated is 3x squared plus 1, not just x squared. So then what you need is the 6. So if you put the 6 in here, then you need to put 1 over 6 on the outside. Which means then that this integral is now 1/6 times the integral of 8 to the u power du, and you have everything you need. And that is going to be 1 over 6 times 8 to the u power times 1 over the natural logarithm of 8, which ultimately is going to be 8 to the u power over 6 times the natural log of 8. And you can't simplify that except to plug back in for u. So there is your integral. 8 to the power 3x squared plus 1 over 6 times the natural log of 8 plus the constant. So now we're ready for problem number 11. And problem number 11 tells us to find the area of the region enclosed by f of x equals x squared minus 4 and g of x equals 1 minus x squared. Now you can find the intersection points algebraically. It's not hard to do. You can also find the intersection points by graphing it, which unless you know your graphing properties pretty well, you're going to need to do that anyway to determine which function's on top. Actually, the function that's on top is going to be g of x, because that is a parabola that opens down, and f of x is a parabola that opens up. So if you choose to sketch this by hand, then what you find out is that 1 minus x squared means it has a y-intercept of 1. And actually, I'm going to mark this off in 2's. Because it'll make our graph a little bit bigger. So this y-intercept is going to be 0, 1. And then it's simply the upside down parabola. So at this point, and I'm not telling you this is perfect, this is a sketch. There's that one. And then this one has a y-intercept of -4. So it looks like this. And the area that we're looking for is the enclosed area. So the x values where this intersection takes place is going to be this plus or minus 5/2. So the actual integral is from negative square root of 5/2 to the positive square root of 5/2, which by the way comes out to be about 1.58, of 1 minus x squared minus x squared minus 4 dx. And you don't really need to do any more than that to do the problem, because you can then plug it into your calculator. And there's a couple of different ways to do it. The first thing we would do, of course, is plug in the two functions into your calculator. And since you don't know where it might intersect, then we're just going to do a standard window zoom 6, and then we'll refine from there. So you can actually do the entire problem from this window if you want to. You can make it smaller if you want to. I'm going to choose just to do it from here. I'm going to hit trace, and I see immediately that the bottom curve is x squared minus 4, and that the top curve is 1 minus x squared. So I'm going to do the integration from this curve minus this curve. So I'm going to turn both of those off. And I'm going to go back to the, well, no, let me leave those on so we can find our intersection points. So we'll go to the Calc menu, choose number 5, intersect. And it says one of the intersections is 1.58. Please do not round that off to 1.5. It's not 1.5. It's 1.58 or 1.6. And the other intersection point is negative 1.58. So if you want to do the integration, it doesn't work if you try to do it from these two graphs, which is the point. What you actually have to do is you're going to have to go back to your y equals menu. And you're going to have to subtract 1 minus x squared minus x squared minus 4. If you want to actually do that integral on screen. Now you can do it correctly from here. And there is your correct answer. You can also do this from the home screen. And since I've already got it typed into Y1 so that I could do it on the graphing screen, then you get the answer that way. Or you can do the entire integral using the exact intersection points if you want to do that. And if I'm going to do that, I'm going to also show you how to do it on the TI-84. So, and actually, let's just do that one without even entering it in. We're going to go Math, Integral. And my TI-84 is an older one, so it doesn't do the nice integration method. But still, we're going to have, in parentheses, 1 minus x squared, subtract x squared minus 4. That's our function with respect to x from, and if you want to do the exact limits of integration, it will be negative square root of 5 over 2, or 2.5, to positive square root 2.5 and what did I do? I made it mad. And you still get 10.51 roughly, 10.541. So there's all the different ways you can do that problem. And you can do it totally by hand if you want to. And since this simplifies, actually, this was a place where algebraic simplification would be simpler. 1 minus x squared would be minus 2x squared. Plus 4 would be 1 plus 4 is 5 dx. This would actually make your integration simpler. So that would be negative 2x to the third divided by 3 plus 5x evaluated at negative square root of 2.5 and positive square root of 2.5 for x. And you're still going to come out with the same thing. I'm not going to do all the arithmetic. It's about 10.4 or 10.54. So, last problem. Find the area of the region between the x-axis and the graph of f of x equals x times e to the x squared from 0 to 2. Basically, we're being asked to find the integral of x e to the x squared dx from 0 to 2. Again, this is a 15.4 problem. The other one was 15.5. And you probably want to graph that for the simple fact that if you don't, you're not going to know if some of it is going to be below the x-axis or not. And I see that it looks like that, and the part I need to see doesn't need really to go much beyond from negative 1 to 3. And since I'm not terribly interested in what's going on in the negative part, since I don't need to see that far down, I'm just going to go to negative 2. And so here I see that I'm looking for the area from here on up, and it probably would be helpful to go on up to maybe 20 to get a better idea. Okay, and apparently it's still going to go up from there. I could make my life easier if I would just put in x equals 2 and see how high that goes. So, but we're looking for an area that looks roughly like this. Again, this doesn't have to be perfect. It looks kind of like that. And none of it is below the x-axis, so we could, you know, actually do this integral by hand with not much problem. Would require a u substitution. So we would need a 2 here and a 1/2 out here. And the integral of e to the u du is e to the u du. And since u is 2x, and we're going to evaluate that at 0 and at 2. So that's going to be 1/2 e to the 2 times 2 is 4. minus 1/2 times e to the 2 times 0 is 0, which is still 0, which means this is going to be minus 1/2. And this is going to be e to the 4th over 2. And that is the answer that I put on your answer sheet, which is the correct answer. Or you can do the entire integration on the calculator. That's fine too. And we get the same answer once again. So, hopefully this helps you with those. I will get your grades posted in the folder. I do have completely corrected tests that I will be scanning and posting in the folder as well. But I will also be on campus tomorrow from 10:30 to 12:30, and I will have your exams with me if you would like to come pick them up at that time. Have a good rest of the afternoon, guys.